Welcome to this explainer. If you've been watching the AI infrastructure market over the last few years, there's really been one undisputed heavyweight champion. But today, we're putting on our financial analyst hats because we are looking at a massive strategic shift in the silicon landscape. See, for a decade, Google built a chip that quietly powered its own data centers, the Tensor Processing Unit. It was basically an internal tool. But recently at Google Cloud Next, they completely pulled back the curtain on the 8th generation of that program. And the numbers, the architecture, and honestly the overall strategy, they signal a total tectonic shift in the market.
And that brings us to the core thesis question we're tackling today. Is the incumbent's dominant moat finally starting to crack? What makes this announcement so genuinely exciting isn't just the raw computing power, though we'll get to that. It's the fact that Google's quiet internal chip development has just resulted in a very public, highly calculated move. For the very first time in the history of the TPU program, Google is actually shipping two completely separate chips in a single generation. It is a direct, head-on challenge to the entire status quo of AI hardware.
Okay, let's dive into this. Here is our market analysis framework for today. First, we'll look at the era of specialization. Then, the TPU-8T for training, followed by the TPU-8i for inference. After that, we'll cover Google's networking edge, their vertical integration and supply chain, and wrap up with the long-term market outlook.
Starting with Section 1, the era of specialization. Why the one-size-fits-all AI chip is officially dead.
So for a long time, the hardware philosophy in this space was pretty simple, right? You build one massive chip, you train your model on it, you run inference on it, and you call it a day. But the fundamental problem with scaling AI today is that the demands of training massive models are now completely incompatible with real-time inference at the hardware level. It basically comes down to the workload. Training is a marathon. You want maximum throughput, enormous memory, and the ability to just throw insane amounts of compute at a problem for weeks on end. But inference, and especially this new wave of agentic AI we're seeing, that is a sprint. Agentic AI doesn't just sit there waiting for a prompt. It's running multi-step workflows, it's looping back on its own outputs, and deciding what to do next in real time. It demands ultra-low latency. Google recognized this deep incompatibility, and instead of compromising with a middle-ground chip, they just split the architecture entirely.
Let's look at that split, starting with Section 2, the TPU-8T, the training marathon, built for massive pre-training.
All right, let's look at the specs of the TPU-8T. And honestly, the numbers here are just absolutely staggering. A single superpod packs 9,600 chips into one massive cluster. It delivers 121 exaflops of compute, but I want you to notice that final metric on the screen, 2 petabytes of shared high-bandwidth memory. I just want to let the sheer scale of 2 petabytes of memory in a single cluster sink in for a second. That is wild. For compute-bound workloads, where just feeding data to the beast is the hardest part, this massive shared memory pool is essentially a dream come true for researchers who are training the next generation of massive frontier models.
But look, raw power isn't enough anymore. It's all about efficiency. And how Google handles data bottlenecks is really where the magic happens here. Right at the heart of the 8T is something called the sparse core. This is a specialized accelerator designed specifically to handle embedding lookups. If you follow AI architecture at all, you know that mixture of experts, or MO models, are kind of the dominant architecture right now, but they create these notoriously painful, totally irregular memory access patterns. Well, the sparse core just offloads all that mess. It keeps the main compute units busy actually computing, instead of sitting around waiting for data. Plus, it introduces native FP4, that's 4-bit floating point precision, which essentially doubles the throughput of the matrix multiply unit without losing any model accuracy.
Now, let's put our investor hats back on for a moment. When you compare this to the previous generation, which was codenamed Ironwood, the TPU-8T delivers a 2.7 times improvement in price performance for large-scale training. That is an absolute game changer. I mean, for cloud customers who are renting these pods and paying by the hour, a nearly 3x leap in efficiency directly heavily impacts the bottom line of every single AI startup and enterprise trying to build a foundation model right now.
Moving to Section 3, the TPU-8i, the inference sprint, engineered specifically for agentic AI. I have to say, I am incredibly enthusiastic about this particular chip because it is such a radical architectural departure from the norm. Just consider the difference in memory architectures. While the 8T we just talked about uses massive shared HBM for pre-training, the 8i takes a completely different route. Google tripled the on-chip SRAM to 384 megabytes and then loaded each individual chip with 288 gigabytes of HBM. Why do that? Well, it's to solve the KV cache problem.
You know when you use an AI and it suddenly feels sluggish during a really long multi-step conversation? That is often a KV cache bottleneck. The AI is literally struggling to hold on to context. The 8i was specifically sized to solve this exact problem at production scale, preventing those sluggish responses during complex agentic workflows.
Now, what's truly fascinating is how Google actually swapped out physical components on the silicon to fit the mission. Remember that sparse core from the training chip we literally just talked about? Yeah, they completely ripped it out of the 8i. Instead, they replaced it with something called the Collectives Acceleration Engine, or CAE. This block is designed entirely for all-to-all communication. When you have multiple specialized AI agents coordinating in real time to solve a problem, they need to talk to each other instantly. The CAE facilitates that rapid agent-to-agent coordination natively on the hardware.
So what is the result of all this hyper-specialization? Try an 80% better performance per dollar specifically for inference workloads compared to the previous generation. That is a massive single-generation jump, cementing the AI's value proposition for anyone looking to actually deploy models profitably to millions of end users.
Okay, Section 4, Google's Networking Edge, Scaling Beyond the Limits.
You see, network topology is the absolutely crucial battleground right now for capturing market share. Let's take a totally impartial look at the sheer scale difference we're dealing with. Nvidia's NVLink topologies, which by the way are phenomenal and totally dominate the commercial space right now, currently top out at 576 GPUs in a single deployment. Meanwhile, Google's new data center fabric, which they call Virgo, can scale to over 1 million TPU chips across multiple sites in a single training cluster. And it pushes 47 petabits per second of bisection bandwidth. That means the cluster can shuttle massive amounts of data from one side to the other instantly, without bottlenecking. Now, I want to be clear here. Nvidia is absolutely still the reigning champion of the commercial market. But at sheer cluster scale, Google is playing a totally different game.
And within those clusters, speed is literally everything. Google has achieved a 56% reduction in maximum network hops, dropping from 16 hops down to just 7. When tokens are getting routed constantly across different expert chips in a mixture of experts model, you just cannot afford to wait on slow network paths. Reducing these hops translates to up to 5 times lower latency. For agentic AI, where speed is the whole point, this is make or break.
So how did they actually do it? By completely abandoning their old 3D torus interconnect topology that they've relied on since their second generation. They replaced it with BoardFly, which is a new 3-tier architecture inspired by academic Dragonfly networks. It's designed from the ground up to eliminate routing bottlenecks entirely. It is a really bold, highly strategic maneuver tailored specifically to conquer that fast-paced inference sprint we talked about.
Moving on to Section 5, Vertical Integration and Supply Chain, Controlling the Full Stack. Google isn't just selling a chip anymore. They are selling what they call the AI hypercomputer. Let's walk through the stack. Step 1, the host CPU. For the first time, they've integrated their own custom ARM-based CPU called Axion. Step 2, the accelerators, the 8T and 8i. Step 3, the Virgo and BoardFly networks we just covered. And finally, Step 4, the software frameworks developers already know and love, like JAX and PyTorch. Because Google now owns this entire stack, they can claim up to 2 times better performance per watt compared to mixing and matching vendors. When you design everything together like this, you unlock efficiency gains that are honestly just physically impossible when you're cobbling together third-party components.
And let's evaluate how this builds into their broader business strategy, because this is huge. They are completely de-risking their supply chain. For a decade, Broadcom had an exclusive partnership with Google for the TPU program. Well, that exclusivity is officially over. MediaTek has now joined as a silicon design partner. Both chips are being fabricated on TSMC's cutting-edge N3 process and use top-tier HBM3E memory. Bringing a giant like MediaTek into the fold gives Google incredible leverage, scale, and a vital diversification move that the financial markets absolutely should not overlook.
Finally, Section 6, the long-term market outlook. The DeepMind co-design philosophy.
This quote captures the broader philosophical shift perfectly. Every spec was derived from real model requirements, not from trying to make a benchmark look good. Google built these chips in direct lockstep partnership with Google DeepMind. The SRAM size on the 8i, the bandwidth on the Virgo network. These weren't just arbitrary targets to look good on a spec sheet. They were built to natively match the incoming wave of agentic AI. The hardware is quite literally mirroring the software.
Which leaves us with this very clear takeaway. Specialization wins.
The era of doing everything on one giant chip is officially over. Splitting architectures into training and inference is a massive philosophical bet that to win the next decade of AI, your infrastructure must perfectly mirror real-time planning, reasoning, and those multi-step looping workflows.
So, I want to leave you with this final, provocative thought. As we look at these immense price-performance gains, the totally specialized architectures for training versus inference, and a completely vertically integrated, de-risked supply chain, how will the AI hardware market share actually shift by Q4? Will the ultimate victor of this incredible AI boom be the incumbent giant, or this vertically integrated challenger who just entirely changed the rules of the game? Let that sink in, keep learning, and I'll see you in the next explainer.